you ready to go through it?
Yes, sir.
Good.
Looking at 3 different
You got it?
I think so.
All right, we'll go ahead and do this. So me probably labeling this initial speed here might have been a little misleading. You can do it, what you could do is you could figure out this initial speed, but then you don't know what this height is. I guess you could figure it out. And then see how far it would go up at that point, right? You could do that. Or we could just say we have spring force and we have gravity force. Those are the only two things that do any work here. Both of those forces are what we call conservative forces. We can introduce kinetic, or we can introduce the potential energy for those. And if we have two different forces with two different types of potential energy, we just add those two potential energies. Then say that the total energy is conserved. That makes sense?
Yeah.
So what I'm going to do is I'm going to call this the initial position. And then when this ball gets up to its maximum height and is at rest, I'm going to call this the final position. Okay? And then I'm going to just look at how the total energy is the same at the initial and the final positions. So kinetic energy initial plus potential energy initial is equal to the kinetic energy final plus the potential energy final. All right? What's the kinetic energy initially?
0.
What's the kinetic energy finally?
0.
All right, very good. So, potential energy initially, it'd be 1/2 K times D squared plus energy, whatever the initial height was. I'm going to call this 0. This I'm going to define my 0 point.
I thought that's what we're looking for.
That'd be equal to
Oh, the final. Okay.
1/2 K times the distance final that the spring is stretched. What's this? It's at its equilibrium point after it's released, right?
Mm-hmm.
0 plus mgh final. I'll just say is h. So this is 0. This is this is the total potential energy. So I would get 1/2 K D squared is equal to mgh. You see how I got that? I'm interested in this height, right?
Yes.
So I could do 1/2 K D squared over mg is equal to the height. Then I can plug in numbers. So that'd be 1/2 K, which was 100 per meter. D, which was 5 centimeters. That's how much the spring was compressed. So that was 0.05 meters squared. M, which is 100 grams, so that's 0.1 kilograms.
Since K is 100.
And then H, and then G is 9.8 meters per second squared. So that's H. When I do that, what do I get?
Like about 0.128. Yeah. Same.
Really?
I got 122.5, but I don't
What's
know.
that?
I might have done it.
I got 0.128 as well.
Oh, 0.128. Okay.
Meters.
12 centimeters. We didn't go up very high, did we? So. get that?
That number that you have on the bottom, it's the meters per second. You gotta put it on there. What-
9.8, that's the G.
It's 9.8. Okay.
All right. Everyone understood what we did? The real key step is just starting out with energy conservation, and then noticing that, and then realizing that if I have two conservative forces, I can talk about the, I can just add the potential energy to the E. That comes from the fact that potential energy is the negative of the work done by that force. And I add all the works by individual forces to look at the change in kinetic energy. Okay, so you just add potential energies of the springs and gravity forces. Those are the only conservative forces we'll ever deal with. Yeah.
One more question. Why did we make the 1/2 kV finals the squared 0?
Oh, because the spring is at its equilibrium position. D is the distance from its equilibrium position, where it's not stretched or compressed. Is that good?
With the potential energy, is it just because it's going on the vertical axis that we add the MGH? Is that always included when you're talking about that, or?
Well, yeah, I mean, you would include whatever the potential energy is. Like, and there's, in gravity, there's always that. We didn't have to do it with here because H didn't change, right? So I might as well just take H to be 0 here and not worry about it. What's that? Okay, are we good? You want to do another one?
Could you also have done it by doing, solving for V naught and then doing another KIPI
Yes, you could have done that.
and then just plug that in to
Yes,
solve for
you could
H?
have gotten the same answer. Yep. That would work. All right. Well, now we better talk about simple harmonic motion. So this is what the chapter is about after all, but we have to understand springs a little bit. So simple harmonic motion. Sometimes that gets abbreviated like SHM, okay? Or simple harmonic oscillators are SHO. So, all right. So basically, here's the idea. So say I have a mass on the spring. Let's say that it's at its equilibrium position. Here, I'm going to call this X naught, equilibrium position. If I stretch it a little bit from equilibrium, so I'm going to draw that. Let me see if I can get a piece of chalk that I can distinguish the non-equilibrium from. So if I stretch it out like this would be X, and then this would be X minus X naught, which is the distance stretch, right? Let's say I stretch it out like that and let it go. All right. What would happen is, immediately it would accelerate back here, right? Then it would start to compress the spring, come to rest at some point over here. The spring force would be pushing that way, accelerate back over here, and it'd go back and forth, like this. That makes sense? As it's going back and forth, it has potential energy here. When it's going to its equilibrium position, it has no potential energy, but it has kinetic energy. Over here, it gains potential energy again and eventually loses all its kinetic energy. Turns around and comes back, gains kinetic energy, loses potential energy, and the potential energy and kinetic energy trade off. Make sense? Well, I'm going to call the spring constant K and this M, the mass M. Here's what I can do. I can kind of, it's tough at this level to really come up with a formula for how long, what we want to do is we want to figure out how long this motion takes. But we can come up with an argument that comes pretty close to giving us a correct formula, and at least gives us something that looks very good. And I'll just give you the correct formula. So when I stretch it out here, I have a potential energy equal to 1/2 K x minus x naught squared. When it's over here, I have a kinetic energy equal to 1/2 m v squared. And each of these is the total energy of the system, because over here there's no kinetic energy, over here there's no potential energy. So these two things are equal to each other. So I get 1/2 m. This is the V max, the maximum speed squared, is equal to 1/2 K x, the maximum stretch from equilibrium squared. Now this V, we know that for if you don't have acceleration, and unfortunately in this case, of course, we have acceleration. But if you don't have any acceleration, the V during a time is going to be the change in distance divided by the time. So I might call the change in distance, I'm just going to write it something like this. This is a little bit misleading, because this would indicate that you don't have any acceleration. Whereas of course we do, because this is accelerating here, going here. But what we're trying to do is just kind of get a sense of things. Okay. We can say the V is not equal to this, goes like that. Very misleading. Distance over time. Yeah. What's that? I haven't done anything with this time yet. I'm just indicating that we have a velocity that's a distance over a time. So, if it takes a time to go from here to here, average velocity would be this distance divided by the time it takes to go from there to there. Okay? So maybe this t, you can say, is the distance to go from its maximum position to equilibrium position. Now this v, of course, won't be, if I just wrote this isn't quite the maximum velocity, because we've had acceleration during this time. This will actually probably be about half the maximum velocity. If I had constant acceleration, it would be half, but I don't. So it's on the order. That's what this little tilde thing is. If I plug this into here, I'll get that 1/2 m times x minus x naught squared over t squared is on the order, or approximately, goes like 1/2 k x minus x naught squared. These x minus x naughts I can divide through on both sides of this. I'll treat this as an equal sign a little bit. I can also get rid of that 1/2. And I can bring this t over to here, like that. So what I end up with is that t squared, which is a time on the order to go from here to here, is something like m over k. So T be something like square root of M over K. Now again, this is very, very rough argument. You need calculus to do this properly. So we're not doing that properly. But this T, the time to go from here to here, is maybe 1/4 of the time it takes to go from here to here to here to here to here. You see that? So I'm going to call that the period of motion. So T about 1/4 the period of motion. This T called the period. Big T, I'll call period from here at this. Hopefully it'll be clear. So you get T, big period is actually on the order of 4 square root of M over K. The correct formula when you deal with calculus and everything like that is actually the period of motion is equal to 2 times pi times the square root of M over K. This is the real formula. So this is the formula for simple harmonic motion, that the period of motion, you go from here over to here and then back to its initial position, is going to be this. 2 pi times the square root of the mass of the object on the end of the spring divided by the spring constant.
So,
Something.
what's the, after the 2 right there?
That's
Pi.
2 pi.
Pi.
So using our very simplistic argument of energy conservation and not doing this properly, we got fairly close, and at least we realized that, you know, this, it has to be like square root of M over K. That's actually the only things in the system that have the proper units for time. So you can guarantee it'll be like this. And then the constant will be a little different, 4 versus 6.2. And that's from calculus. So here's the question. Oh, I wanted to do a demonstration really quick. All right, I'll be right back.
So we're never going to use
The rest of
No.
them, which if they want.
Only we're gonna use
we're
the
just
real
going
ones,
to use the T
I
equals 2
think.
pi.
It should have the red.
Yeah.
Right here. Okay. All right, at this point, this is the equilibrium position at this point. And we're not gonna, the fact that it's horizontal versus vertical, and that there's a little gravity potential energy here turns out to affect what we're about to do. So I have a 50-gram mass at the end of here. And if I let it go, see how it goes up and down? Anyone remember what the spring constant we got for this was? So yesterday we measured the spring constant directly. What was it?
9.6.
What was it?
9.65.
Okay, so K from yesterday was 9.65. You know, we're gonna do it pretty rough. Let's do about 9.7. Actually, this is probably not rough enough. Newtons per meter.
I'll show you.
All right. Somebody get, so does anyone have a phone with a timer? We can do this really quick. What I'm going to do is I'm going to stretch this down a little bit, and I'm going to let it go. 1 period is when it goes up, it comes back down to its initial position. Can you measure the time for, let's do 5 periods, okay? So you'll count 1 when it comes back, 2, 3, 4, 5, okay? And then, can you do that?
Do it.
On your mark, let's do it. Get set, go.
2, 3, 4,
5. So what's the time for 5 periods?
About 3 seconds.
What was it?
3
Because we
seconds.
started to put it.
3 seconds. Good, so period is 3/5 of a second, right? Now, according to what we have here, that should be equal to 2 pi square root of m over k. Right? Now, let's see if we can figure out a k from this and see if it's anywhere near that k. Okay, this mass we have here is 50 grams. So I'm going to write 3, okay, t divided by 2 pi is square root of m over k. Square both sides. Divide by m. Take reciprocal of both sides. This equals 2k. Okay, plug in 0.05 kilograms here. 3/5, so 0.6 seconds per period there. And then see what you get for k. I think.
Is that a comma?
What's that?
After the K, is that a comma and then M? Okay.
So this should be,
Should it be m divided by this? Oh, never mind.
I think we're good. So this is 2 pi over t. This is about 6 divided by 0.6. That'd be about 10 squared, 100, divided by 0.05. So I'm getting on the order of 20, aren't I?
Wait, how is
Three.
2.6?
3 over 5.
Okay.
3/5 of a second. So what do you guys get?
What's M for mass?
M was 50 grams.
Oh, yeah.
7.5 kilograms.
Yeah. 0.05.
Oh, I do.
So what are you getting?
I got k equals 5.48.
5.48.
Yeah, 4.67. 5.8.
What's that? About 6? 4.6.
I got 4.2.
All right. What do you get?
5.2.
I got 5.48.
We'll do this.
What are you gonna
All right, so you're off by about 50% or 100%.
So what does that mean?
It means that you're on the right order of magnitude.
Oh.
But I'll blame Marshall's trying to.
Oh, okay. Because I was like, is our calculation from yesterday wrong or?
It's all right. See, this is t squared, so if you're off by back one factor back a quarter. It's the off by a factor of a half. And you're pretty well yesterday, did that.
I work at 1 yesterday. Good Lord, are you losing your damn mind?
Well, I just remembered you told me to work at 1.
Yeah.
Okay.
That,
I might just find something.
and sometimes we can